Superalloys are a class of high-performance metallic materials specifically designed to retain mechanical strength, structural stability, and corrosion or oxidation resistance at elevated temperatures. They are indispensable in gas turbine engines, power generation, chemical processing, nuclear systems, and other applications involving severe thermal and mechanical environments. Their performance derives from carefully engineered compositions and microstructures that suppress plastic deformation, creep, oxidation, and phase instability. High-Entropy Alloys, HEA, developed principally in the early 2000s, represent a different philosophy of alloy design. Instead of using one dominant metallic element with relatively small alloying additions, HEAs generally contain several principal elements, often in near-equiatomic proportions. This compositional complexity can produce unusual combinations of strength, ductility, corrosion resistance, wear resistance, and thermal stability. High-Entropy Superalloys, HESA, combine concepts from both classes, particularly the compositional complexity of HEAs, with the precipitation-strengthening strategies characteristic of conventional superalloys. Superalloys. Superalloys are commonly classified according to their principal matrix element into nickel, cobalt, and iron-based superalloys. Although their compositions differ substantially, they share the objective of maintaining useful mechanical properties at temperatures where conventional steels and light metal alloys undergo rapid creep or loss of strength. Nickel-based superalloys. Nickel-based superalloys are the most technologically important superalloys and are extensively used in the hot sections of aero engines and land-based gas turbines. Representative commercial families include Mnemonic, Inconel, Rene, and CMSX alloys. They can operate at temperatures approaching or exceeding 800 to 1000 degrees Celsius, depending on composition, processing, cooling, and service conditions. The baseline material architecture of a superalloy relies on a two-phase equilibrium. It consists of a primary gamma matrix and secondary gamma prime precipitates dispersed within it. Their exceptional performance originates from a predominantly FCC gamma-nickel matrix, strengthened by alloying elements such as chromium, cobalt, molybdenum, tungsten, and rhenium. The most important strengthening phase is the ordered gamma prime phase, nominally Ni3, aluminum-titanium, which possesses an L12 structure and remains coherent with the gamma matrix. In some alloys, particularly IN718, the ordered gamma double prime phase, approximately Ni3 NeB, provides major precipitation strengthening. Carbides such as M23C6, M6C, and MC can additionally contribute to grain boundary and matrix strengthening. The gamma or gamma prime microstructure is particularly important because gamma prime resists dislocation motion and retains substantial strength at elevated temperatures. Modern single-crystal turbine blade alloys exploit this microstructural principle while eliminating transverse grain boundaries, thereby substantially improving creep and thermal fatigue resistance. Cobalt-based superalloys. Cobalt-based superalloys contain cobalt as the principal matrix element and typically incorporate chromium, nickel, molybdenum, tungsten, carbon, and other alloying elements. For example, allocrite, also known as alloy L605 or cobalt L605, is a family of cobalt-based alloys. L605 is a non-magnetic cobalt-chromium-nickel-tungsten alloy possessing good oxidation and corrosion resistance as well as high-strength properties at elevated temperatures. They are valued for high-temperature corrosion and wear resistance and have historically been important for turbine vanes, combustion components, furnace hardware, and biomedical applications. Compared with conventional nickel superalloys, cobalt alloys traditionally rely more strongly on solid solution strengthening and carbide strengthening. Chromium promotes formation of protective Cr2O3 scales, while W and MO provide solid solution strengthening. Their relatively high melting temperatures and good hot corrosion resistance make them attractive for components exposed to aggressive high-temperature environments. An important modern development is the discovery of CO-Al-W-based gamma, or gamma prime superalloys, in which an L12CO3 aluminum-tungsten type gamma prime phase provides precipitation strengthening analogous to the gamma/gamma prime microstructure of nickel superalloys. These alloys demonstrated that the powerful precipitation strengthening concept of Ni-based superalloys could potentially be extended to cobalt-rich systems. Iron-based superalloys. Iron-based superalloys occupy an intermediate position in cost and high-temperature capability. They commonly contain Fe-Ni-Cr with additions such as molybdenum, titanium, aluminum, and niobium. Examples include A286, Incolloy 800, Inconel, or iron-nickel-chromium families, and Incolloy 825. A 286 is a particularly important precipitation-strengthened iron-nickel-chromium alloy containing aluminum and titanium. Depending on composition, iron-based superalloys can employ solid solution strengthening or precipitation strengthening through gamma prime and, in some compositions, gamma double prime. They are generally used at lower temperatures than the most advanced nickel-based turbine alloys. Still, their lower cost and good combination of strength, corrosion resistance, and fabricability make them attractive for structural components, fasteners, chemical equipment, and power generation systems. Principal strengthening mechanisms. The outstanding performance of superalloys results from several complementary mechanisms. Solid solution strengthening. Large or chemically different solute atoms such as tungsten, molybdenum, rhenium, and chromium distort the crystal lattice and impede dislocation motion. Precipitation strengthening. Fine coherent or semi-coherent intermetallic precipitates, particularly gamma prime and gamma double prime, strongly obstruct dislocation motion. Grain boundary strengthening. Grain boundary carbides and controlled grain structures can suppress grain boundary sliding and creep. Conversely, eliminating grain boundaries through single crystal processing can provide major creep advantages in turbine blades. Creep resistance. Creep is controlled through stable precipitates, refractory element additions, optimized grain structures, and resistance to dislocation climb and diffusion. Nickel superalloys are remarkable because they retain creep strength at temperatures approaching a substantial fraction of their melting temperature. Oxidation and corrosion resistance. Chromium and aluminum are particularly important because they form protective oxide scales, principally chromium oxide Cr2O3 and alumina Al2O3, which limit further oxygen transport into the alloy. Processing and limitations of superalloys. Superalloy performance is strongly dependent on processing history. Conventional routes include casting, forging, solution treatment, aging, powder metallurgy, and, increasingly, additive manufacturing. Directional solidification and single crystal casting are especially important for advanced turbine blades. The same alloy chemistry that produces exceptional high-temperature performance can also create processing difficulties. Nickel-based superalloys, for example, are difficult to machine because of their high strength, low thermal conductivity, work hardening, and tendency to generate substantial cutting temperatures. Welding can also be challenging because precipitation-strengthened alloys are susceptible to heat-affected zone liquation and hot cracking. These limitations motivate continued development of advanced joining, machining, coating, repair, powder processing, and additive manufacturing technologies. High-Entropy Alloys. HEAs introduced a major change in alloy design philosophy. Rather than defining an alloy around a single base metal, HEAs generally contain 5 or more principal elements, frequently in concentrations between approximately 5 and 35% each. The well-known Cantor alloy, equiatomic chromium, manganese, iron, cobalt, nickel, is a landmark example. The original HEA concept emphasized high configurational entropy of mixing. Delta S mix equals minus R sum of Xi natural log Xi. For an equiatomic 5-component alloy, the configurational entropy is approximately 1.61 R. High entropy can favor disordered solid solution phases relative to some competing ordered compounds, although modern understanding recognizes that entropy is only one factor governing phase formation. Enthalpy of mixing, atomic size mismatch, valence electron concentration, kinetic effects, and processing history can be equally important. Importantly, not every HEA is a single-phase solid solution. HEAs may contain FCC, BCC, HCP, ordered B2 or L12 phases, intermetallic compounds, or multiphase microstructures. This compositional flexibility is now deliberately exploited to optimize properties rather than maximize configurational entropy. Why HEAs are attractive. HEAs can exhibit unusual combinations of mechanical and environmental properties. Depending on composition and microstructure, reported characteristics include high strength, good fracture toughness, excellent wear resistance, corrosion resistance, thermal stability, and useful mechanical properties at cryogenic or elevated temperatures. The Cantor alloy is particularly notable for its exceptional low-temperature toughness. Other HEAs, especially refractory metal-containing systems such as niobium, molybdenum, tantalum, tungsten, and molybdenum, niobium, tantalum, vanadium, tungsten type alloys, have attracted attention for high-temperature structural applications because of their high melting temperatures and strength. However, the properties of HEAs are highly composition and microstructure dependent. The concept of a universal high-entropy effect should therefore not be interpreted as guaranteeing superior performance. Phase constitution. Defects, grain size, precipitation, and processing remain decisive. High-Entropy Superalloys. High-Entropy Superalloys HESA seek to combine the advantages of HEAs with the well-established strengthening architecture of conventional superalloys. A particularly important strategy is to develop an FCC gamma matrix containing ordered L12 gamma prime precipitates, analogous to the gamma/gamma prime microstructure of Ni-based superalloys. Typical HESA compositions may incorporate nickel, cobalt, iron, chromium, and refractory elements such as molybdenum, tungsten, and tantalum. The design objective is to obtain a chemically complex matrix while retaining a stable population of strengthening precipitates. Thus, instead of relying solely on configurational entropy, HESAs use solid solution strengthening, precipitation strengthening, grain boundary engineering, and oxidation control simultaneously. This strategy is particularly attractive for temperatures approaching or exceeding 1,000 degrees Celsius, where conventional superalloys face increasing problems with oxidation, precipitate coarsening, phase instability, and loss of creep strength. Future outlook. Superalloys remain the benchmark materials for demanding high-temperature turbine applications because decades of alloy development, processing optimization, coatings, and component design have produced highly reliable materials. HEAs and HESAs represent a broader design space, rather than an automatic replacement for conventional superalloys. Their principal opportunity lies in discovering combinations of strength, ductility, thermal stability, oxidation resistance, and damage tolerance that are difficult to obtain using conventional alloy design strategies. The principal challenges for HESAs include compositional complexity, expensive or critical alloying elements, segregation, manufacturability, long-term phase stability, oxidation/corrosion behavior, and establishing reliable processing structure-property relationships. Future progress will therefore depend on integrating thermodynamic modeling, machine learning, advanced characterization, additive manufacturing, and targeted microstructural engineering. In summary, superalloys represent the mature state of high-temperature alloy engineering, whereas HEAs provide a fundamentally expanded compositional design space. HESAs attempt to bridge these approaches by combining multi-component alloy chemistry with the precipitation-strengthened gamma/gamma prime architectures responsible for the exceptional performance of modern nickel-based superalloys.